A tropical storm sits 200 miles offshore. Wind speeds 60 miles per hour. Manageable. Forecasters call it a tropical storm. Evacuation orders are on hold. 24 hours later, it hits land at 175 miles per hour. That is a Category 5 hurricane, and nobody saw it coming. This is happening more often. Storms are transforming overnight into monsters that models cannot predict and coastlines cannot prepare for. Tonight we go inside the science that has veteran forecasters genuinely scared. We will follow a plane flying into an eye wall, watch a storm rebuild itself from the inside, and find out why the system designed to protect millions of people keeps failing at the worst possible moment. If you want more videos like this, hit like and subscribe. It helps more than you know. Stay with us. We begin now. Picture a campfire. Small, controlled, manageable. Now imagine someone dumps a full tank of gasoline on it in under a minute. The flames don't just grow, they explode. That is what rapid intensification does to a hurricane. The official definition is straightforward. A storm goes through rapid intensification when its maximum wind speeds climb by at least 35 miles per hour in a single 24-hour window. 35 miles per hour sounds like a number. Here is what it means in real life. A tropical storm sitting at 60 miles per hour winds becomes a Category 2 hurricane overnight. A Category 2 becomes a Category 4 by morning. The storm that looked manageable on the evening news is a catastrophe before sunrise. Forecasters do not fear the storms they can track. They fear the ones that change faster than their tools can measure. And rapid intensification is the fastest change in weather science. Here is why that matters directly to you. Emergency managers need 48 to 72 hours to move people out of a danger zone. Hospitals need time to evacuate patients. Nursing homes need buses and drivers and coordination. When a storm jumps from a tropical storm to a major hurricane in one day, that window collapses. People who had time to leave suddenly do not. The National Hurricane Center watches wind speed data around the clock. Scientists sit at screens tracking pressure readings, satellite images, and computer model outputs. Their job is to give communities enough warning to survive. And for decades, that job has gotten harder in one specific area. Track forecasts, meaning where a storm goes, have improved dramatically. 50 years ago, forecasters could barely predict a storm's path 3 days out. Today, they can do it 5 days out, with impressive accuracy. But intensity forecasts, meaning how strong a storm gets, have not kept up. The math behind strength is messier. The variables are smaller, harder to measure, and interact in ways that even the best supercomputers struggle to simulate. This gap between track skill and intensity skill is where lives fall through. Scientists began noticing a troubling trend around 1982. Rapid intensification events were becoming more frequent. More storms were getting less warning. At first, researchers debated whether it was a natural cycle or something more permanent. That debate is still happening. But the events keep coming, and they keep catching forecasters off guard. Something else is happening too. The storms that rapidly intensify are not weakening as fast after landfall as older storms did. They are holding their strength longer, staying dangerous further inland. The gasoline analogy goes further than just the ignition. The fire is burning longer too. There is one more thing that makes rapid intensification uniquely terrifying. It requires a specific combination of ingredients to happen: warm water, low wind shear, moist air, minimal dry air intrusion. When those conditions line up, the storm does not gradually grow. It lurches. It skips categories. It becomes something different almost instantly. Each of those ingredients has its own science, its own story, and some of them are becoming more common as the ocean warms. What powers all of this starts below the surface of the water, something sitting miles deep that most people have never thought about. And it is changing. Think about a car engine. You pour in fuel, the engine burns it. And that energy moves the car. Take away the fuel, and the engine stops. Simple. A hurricane works the same way. The fuel is heat. The engine is the storm itself. And the tank is the ocean. Here is how it starts. Warm ocean water evaporates. That water vapor rises into the atmosphere, carrying heat with it. As it climbs, it cools and condenses back into clouds and rain. That condensation releases energy. The energy warms the surrounding air. Warm air rises faster. More ocean water evaporates. More vapor rises. More condensation. More energy. The loop feeds itself. As air rushes upward in the center of the storm, it creates a low-pressure zone at the surface. The surrounding higher-pressure air pushes in to fill the gap. That inrushing air spins because of the Earth's rotation. In the northern hemisphere, it spins counterclockwise. That spin is what makes the storm a hurricane rather than just a really bad thunderstorm. The faster the air rises at the center, the lower the surface pressure drops. The lower the pressure, the harder the surrounding air pushes inward. The harder it pushes, the faster the winds spin. This is why meteorologists watch pressure so closely. A dropping pressure reading is the storm accelerating. Now here is the part that separates a manageable storm from a catastrophic one. The efficiency of the engine depends entirely on how much heat the ocean provides and how well the storm can vent its exhaust. In an engine, the exhaust has to go somewhere. In a hurricane, the exhaust is warm air that rises through the storm's center and spreads outward high in the atmosphere. If something disrupts that outflow, the engine chokes. If the outflow runs clean and uninterrupted, the engine roars. Scientists call a perfectly organized, efficiently venting hurricane an annular storm. The eye wall is tight and symmetrical. The rain bands wrapped cleanly around the center. The whole structure looks almost geometric from a satellite. These storms are the ones that resist weakening even when conditions should slow them down. Most storms never reach that level of organization. They wobble, they tilt, their eye walls break down and rebuild. But when all the conditions align, the engine runs at full power. One visual helps make this real. Picture the ocean as a stove burner. Most of the time the burner is on low. The water is warm but not scorching. The storm gets some energy but stays modest. Now imagine someone cranks the burner to high and leaves it there. The water heats up faster, deeper. The storm sitting on top of it suddenly has unlimited fuel. It does not grow gradually. It accelerates. For most of the last century, the ocean had a natural limit. Even when the surface was warm, cooler water sat just below. When a storm churned the ocean with its winds, it dragged that cold water up. The cold water cooled the surface. The fuel supply dropped. The storm slowed down. That cooling effect was one of nature's brakes on rapid intensification. What is happening to those brakes right now is something scientists confirmed only recently, and it makes the next ingredient far more dangerous than it used to be. There is a threshold, a line in the ocean that separates a tropical disturbance from a potential catastrophe. 80 degrees Fahrenheit. That number, confirmed by decades of research, is the minimum ocean surface temperature a tropical storm needs to sustain itself and grow. Below 80 degrees, a storm starves. The fuel supply drops too low. The engine sputters. The storm weakens and eventually falls apart. Above 80 degrees, the storm feeds. But here is what makes this more than just a simple cutoff. The relationship between ocean temperature and storm strength is not linear. It does not go up in a straight line. It curves upward sharply. An ocean at 82 degrees gives a storm noticeably more energy than one at 80. An ocean at 85 degrees gives exponentially more. Small temperature differences in the upper range of that scale produce enormous differences in storm behavior. Scientists discovered something alarming when they began mapping global ocean surface temperatures over the past several decades. The areas that regularly exceed 80 degrees Fahrenheit are expanding. Patches of the Atlantic, the Gulf of Mexico, and the Pacific that used to hover right around the threshold are now sitting several degrees above it for longer stretches of the year. This matters for a very specific reason. Hurricane season used to have a defined window where conditions were dangerous. It still officially runs from June 1st through November 30th. But the warm water window that powers rapid intensification is getting longer at both ends. Storms forming in May or December are now finding ocean temperatures that would have been unusual even in peak season 40 years ago. There is also a geographic shift happening. Waters that were once too cold to sustain a major storm are warming up. Areas of coastline that historically had a natural buffer, cooler water that kept storms from reaching their full strength before making landfall, are losing that buffer. One way to picture it: imagine a 100-mile stretch of highway before a city. The highway used to be covered in speed bumps. A fast car had to slow down. Now the speed bumps are disappearing one by one. A storm approaching that coastline accelerates instead of slowing. The 80-degree threshold is confirmed science. What sits just below the surface of that warm water, however, is where things get genuinely strange. When forecasters talk about dangerous ocean conditions, they rarely just mention surface temperature. They talk about something called ocean heat content. And ocean heat content is a different measurement entirely. Surface temperature tells you how warm the top layer of water is. Ocean heat content tells you how deep that warmth goes. And depth changes everything. A shallow layer of warm water can be churned away by a storm's own winds. As the storm passes, it stirs the ocean beneath it. If cold water sits just 20 or 30 feet down, that cold water mixes up to the surface and cuts off the fuel supply. The storm weakens naturally. But when the warm water goes deep, that mechanism stops working. The storm churns and finds more warm water, no matter how hard it stirs. This is what forecasters found when they looked back at the most explosive rapid intensification events on record. Almost every single one happened over unusually deep pockets of warm water. And those pockets are not going away. In fact, the next chapter explains exactly why they are growing deeper every year. For most of the last century, the ocean had a built-in speed limit for hurricanes. It worked like this. A storm moves across the ocean surface. Its powerful winds churn the water below. That churning pulls cold water up from deeper layers and mixes it with the warm surface water. The surface cools. The storm's fuel supply drops. The storm weakens. Scientists call this upwelling. It is a natural process. It was one of the main reasons that even powerful hurricanes tended to weaken somewhat before making landfall. The storms were, in a sense, eating their own fuel supply. That brake is failing. Here is why. The ocean does not heat evenly. The warmth added by decades of rising global temperatures has not spread uniformly through the water column. In many regions, particularly the Gulf of Mexico and parts of the Western Atlantic, that extra heat has penetrated far deeper than expected. Instead of sitting in a thin layer at the top, the warm water now reaches 60, 80, sometimes over 100 feet below the surface. When a storm churns that water column, it does not find cold water underneath. It finds more warm water. The brake does not engage. The fuel supply does not drop. The storm keeps accelerating. Scientists confirmed this pattern by comparing satellite measurements of sea surface temperature with data from underwater instruments called Argo floats. These robotic devices drift through the ocean, diving and surfacing to measure temperature and salinity at different depths. When researchers layered that data over maps of rapid intensification events, the overlap was striking. The most explosive storms almost always crossed over regions where warm water extended unusually deep. Here is a comparison that makes this easy to picture. Imagine two campfires. The first one sits on a thin pile of dry wood. It burns hot, but the wood runs out quickly and the fire dies down. The second fire sits on a massive stack of dry wood reaching 10 feet high. It burns just as hot at first, but when the surface wood burns away, there is more below it, and more below that. The fire does not slow down because the fuel keeps coming. The deep, warm water pool in the Gulf of Mexico has been studied extensively. It has a name. Scientists call it the loop current. This is a river of warm water that flows up from the Caribbean, loops through the Gulf, and exits through the Florida Straits. When a storm crosses over the loop current or one of its warm water eddies, it passes over some of the deepest warm water in the Atlantic Basin. Hurricane Katrina crossed a loop current eddy in August 2005. In 24 hours, it went from a Category 3 to a Category 5 storm. That eddy provided warm water so deep that Katrina's churning winds could not cool the surface enough to slow it down. The same pattern appeared before several other catastrophic Gulf storms. The deep warm water is not a random variable, it is a predictable and growing factor in rapid intensification. But warm water alone is not enough. A storm also needs the atmosphere above it to cooperate, and when that atmosphere is perfectly calm, the results are terrifying. Forecasters have a list of conditions they watch: warm water, moist air, storm organization. But one variable sits near the top of that list as both a destroyer of storms and, when it disappears, a trigger for catastrophe: wind shear. The term sounds technical. The concept is simple. Wind shear is the difference in wind speed and direction between the lower atmosphere and the upper atmosphere. At the surface, the wind might blow from the southeast at 20 miles per hour. 8 miles up, it might blow from the west at 60 miles per hour. That difference is shear. High wind shear tears a hurricane apart. Picture a spinning top. As long as it spins on a flat surface with nothing interfering, it stays upright and organized. Now picture someone pushing the top from the side while it spins. The top tilts. It wobbles. It loses its symmetry. If the push is strong enough, the top falls over. Wind shear does the same thing to a hurricane. The upper level winds push against the top of the storm, while the lower level winds push differently at the base. The storm tilts. The eye wall breaks apart. The organized structure collapses. Without that tight, symmetric engine, the storm cannot generate and sustain extreme winds. The shear essentially shuts the engine down. This is why forecasters actually welcome shear during active hurricane season. High shear in the Gulf of Mexico or the Western Atlantic is a form of natural protection. It keeps storms disorganized. It prevents the rapid intensification engine from running at full power. The terrifying condition is when that shear drops away. When upper-level winds and lower-level winds align, when the difference between them shrinks towards zero, the atmosphere becomes what forecasters call a low-shear environment. The storm can stand straight. The eye wall tightens. The outflow at the top of the storm spreads cleanly in all directions without being disrupted. The engine runs efficiently. Combine low shear with deep warm water and high moisture levels, and you have every ingredient for explosive rapid intensification, sitting in one place at one time. Forecasters watch shear maps constantly. They look at models projecting how shear will change over the coming days. When they see a storm approaching a region where shear is forecast to drop dramatically, the mood in a forecast office shifts. The conversations get quieter. The uncertainty widens. Here is the additional problem. Shear forecasts have their own errors. The atmosphere is not a simple system. Upper-level winds can shift faster than models predict. A storm that was supposed to encounter moderate shear that would keep it organized but limited can suddenly find itself in a shear pocket where everything drops away at once. That is when a storm surprises everyone. There is also a subtler effect that researchers have been studying. Some storms seem to partially withstand shear that should destroy them. They tilt, but do not collapse. They fight through the disruption and emerge more organized than they were before. Scientists confirmed this happens. They do not fully understand why some storms survive and others fall apart under identical shear conditions. That remains an open mystery. What happens when all of these ingredients line up perfectly at once over a populated coastline with almost no warning? Has already happened. And the city it happened to was completely unprepared. October 24th, 2023, Acapulco, Mexico. The forecast showed a tropical storm approaching the coast, wind speeds around 70 miles per hour. Forecasters predicted it might reach Category 1 strength before landfall. Authorities issued warnings. Some preparations began. But the threat level on paper looked manageable, a tropical storm making landfall, serious but survivable. What arrived was a Category 5 hurricane. In 24 hours, Hurricane Otis gained 115 miles per hour of wind speed. 115. That is more than tripling in strength in a single day. A storm that looked like a bad rainstorm on Tuesday morning was the strongest Pacific hurricane ever recorded at landfall by Tuesday night. Acapulco had almost no warning. The city of nearly 1 million people had hours, not days. Hotels could not evacuate guests. Hospitals could not move patients. Families in low-lying areas could not get out. The storm destroyed or severely damaged nearly 80% of the structures in the city. The death toll climbed into the hundreds. The economic damage was in the billions. And meteorologists around the world stared at their screens in a state of collective disbelief. This was not a situation where forecasters missed a subtle signal. The models were not just slightly off. Every major forecasting system underestimated Otis by a catastrophic margin. Some models predicted the storm would reach Category 1. The actual peak intensity was Category 5. The gap between prediction and reality was historic. Researchers immediately began studying what happened. What they found was a convergence of every rapid intensification ingredient at once. The Pacific waters southwest of Mexico were running abnormally warm. Not just at the surface, but deep below it. Wind shear in the region dropped dramatically in the 24 hours before landfall. The storm's internal structure reorganized almost instantly once those conditions aligned. The models saw the warm water, they registered the dropping shear, but they could not accurately simulate how quickly the storm's inner core would respond. The intensification feedback loop ran faster than any computer model expected. One factor made everything worse. Otis approached from a direction that gave forecasters less time to gather observational data. Hurricane Hunter aircraft, the planes that fly directly into storms to measure conditions, had limited flight time over Otis before it struck. The data gaps were significant. The models were running with less information than usual precisely when they needed more. Scientists confirmed that Otis represented a genuine failure of the current forecasting system, not a one-time fluke. The ingredients that drove it, deep warm water, sudden shear collapse, a storm approaching faster than observation networks could sample, are all present in other ocean basins. They can combine again anywhere. The disaster exposed a fundamental problem. The tools built to protect coastal populations are excellent at tracking where storms go. They are far less reliable at predicting how strong storms become. And in an era when rapid intensification is growing more frequent, that gap between track skill and intensity skill is the most dangerous gap in weather science. Otis was the clearest example. But the same failure mode had been building inside the forecasting system for years, and the technology meant to fix it has limits that most people do not know about. Weather forecasting runs on math, enormous, complex math. The computers that run hurricane models are among the most powerful on Earth. The National Hurricane Center uses supercomputers that process billions of calculations per second. They ingest data from satellites, weather balloons, ocean buoys, aircraft observations, and ground stations. They solve equations that describe how air moves, how water evaporates, how heat transfers between the ocean and the atmosphere. And they are excellent at one thing: tracking where storms go. Over the last 2 decades, track forecast errors dropped by 75%. A 5-day track forecast today is as accurate as a 2-day forecast was in the 1980s. That improvement saved lives. Communities got more time to prepare. Evacuation orders came earlier and more accurately. Intensity forecasts did not keep pace. The math for predicting storm strength involves processes happening at scales far smaller than track motion. A hurricane moves across hundreds of miles of ocean. That motion is governed by large atmospheric patterns that giant models can simulate reasonably well. But rapid intensification is triggered by processes happening at the scale of miles, sometimes less. Small pockets of dry air, subtle shifts in the storm's inner core, the exact temperature of water at specific depths along a narrow storm path. These small-scale features are what forecasters call the mesoscale. They fall below the resolution of most global models. The grid squares in a global model might represent an area 20 or 30 miles across. A dry air pocket that could dramatically change a storm's behavior might be only 5 miles wide. The model never sees it. Scientists work to solve this by building specialized, higher-resolution models focused specifically on hurricane intensity. These models zoom in on the storm. They run on finer grids. They include more detailed physics. They helped. The improvement was real but modest. The core problem remains. To accurately simulate rapid intensification, a model needs precise, real-time data about conditions inside and around the storm. Ocean temperature at specific depths, humidity levels at different altitudes, wind speeds at every layer of the atmosphere surrounding the storm's core. That data is extremely hard to collect. Weather satellites orbit overhead and measure surface conditions. They give excellent images of storm structure and can estimate cloud top temperatures, but they struggle to see through clouds into the storm's interior. They cannot directly measure what the air is doing at different altitudes inside the system. The models also assume that the ocean beneath the storm behaves in a predictable way. In reality, the ocean has eddies, temperature variations, and salinity gradients that interact with storm dynamics in ways that are still being studied. A model running on averaged ocean data will miss the specific pocket of unusually deep warm water that triggers an intensification burst. When a model misses one of these hidden variables, the error compounds. The initial intensity estimate is off. The model's simulation of the storm evolves in a slightly wrong direction. By the time the storm is 12 hours away from landfall, the model's prediction can be multiple categories off from reality. This is the system that millions of people depend on. The scientists inside that system know its limits better than anyone, and some of them are flying airplanes directly into hurricanes trying to fill the data gaps by hand. There is a group of people whose job is to fly into the most violent storms on Earth, on purpose. They are called hurricane hunters. The official units are the NOAA Aircraft Operations Center and the United States Air Force Reserve's 53rd Weather Reconnaissance Squadron. Their aircraft are specially reinforced turboprop planes built to withstand the violent turbulence inside a hurricane's eye wall. The flights are not calm. Pilots describe flying through an eye wall as the roughest air imaginable, where the plane gets thrown hundreds of feet vertically in seconds, and cockpit instruments rattle against their mounts. The crew works through it methodically. Scientists in the back of the plane monitor equipment and call out readings, while the plane pitches and rolls through winds that would destroy a commercial aircraft. What these planes deploy is the most direct data source in hurricane science. The instrument is called a drop sonde. It is roughly the size and shape of a large water bottle. It contains sensors that measure air pressure, temperature, humidity, and wind speed. The drop sonde is loaded into a tube and ejected from the bottom of the aircraft. A small parachute deploys. The drop sonde falls through the storm, transmitting data back to the plane every single second as it descends from the aircraft's altitude to the ocean surface. That descent takes roughly 15 minutes. In those 15 minutes, the drop sonde captures a vertical profile of the atmosphere directly through the storm. It records what the air is doing at every altitude from 8 miles up to sea level: wind speed, direction, temperature, moisture, pressure, all confirmed direct measurements. This data goes directly into the forecast models. A single well-placed drop sonde gives the model information it cannot get from any satellite. It fills in the vertical picture of the storm that remote sensing struggles to provide. The limitation is coverage. A single flight can drop several dozen drop signs over several hours. But a hurricane is a massive system spanning hundreds of miles in diameter. The plane flies a specific pattern through the storm, typically an X pattern crossing through the eye. The drop sondes land along that narrow flight path. The rest of the storm remains unmeasured. Vast sections of a major hurricane, including areas of the outer rain bands and the ocean ahead of the storm, get no direct observation. The models fill those gaps with estimated values based on surrounding data. When the real conditions in those gaps differ significantly from the estimates, the model errors begin. Researchers have pushed for more aircraft, more flight hours, and more drop signs per mission. The programs are expensive, aircraft are limited, flight time over a single storm before landfall is always shorter than forecasters want. There is a newer technology being tested to help: uncrewed aerial vehicles, essentially large drones that could fly lower altitudes inside a storm for longer periods. Some prototypes have already flown into actual hurricanes on test missions. The data they return is promising, but right now, the hurricane hunters and their water bottle-sized instruments are still the most reliable window into a storm's interior. And one of the things they keep finding inside these storms is something invisible, unpredictable, and capable of completely reversing a storm's trajectory: dry air, and scientists still cannot agree on what it will do when it arrives. Every ingredient scientists track in hurricane forecasting has predictable behavior. Warm water feeds storms, low shear lets them organize, moist air supports their growth. These relationships are confirmed and well understood. Dry air is different. Dry air is exactly what it sounds like: a mass of air with very low moisture content. In a tropical atmosphere where nearly everything is humid and saturated, a pocket of dry air is almost alien, and when it contacts a developing or intensifying hurricane, two completely opposite things can happen. The dry air can kill the storm, or it can get swallowed up and matter almost not at all. Scientists have confirmed both outcomes. They have watched storms fall apart when dry air entered the circulation. They have watched other storms of similar strength in similar positions absorb identical-looking dry air intrusions and continue intensifying without interruption. The difference between the two outcomes remains one of the genuine unsolved problems in hurricane science. Here is why this is so dangerous for forecasting. A model that sees dry air approaching a storm has to make a decision. Does this dry air interact with the storm or not? How deeply does it penetrate? Does it reach the inner core where it can disrupt the eye wall? Or does it stay in the outer rain bands where its effect is minimal? The answers depend on factors that are extremely difficult to measure: the exact dryness of the air mass, the exact boundary where the dry air meets the moist circulation of the storm's own strength, which determines how effectively it can resist intrusion. Current satellite instruments see the signature of dry air in the upper atmosphere. They detect it by tracking water vapor, but they cannot measure it precisely enough to tell forecasters exactly how dry a specific pocket is, how deep it extends, or exactly how far it sits from the storm's center. Drop-sonde data helps, but only where the aircraft flies. A dry air mass sitting to the northwest of a storm gets sampled only if a hurricane hunter specifically routes through it. That takes flight time away from the storm itself. The result is that forecasters often see dry air approaching on satellite imagery and cannot confidently say whether it will weaken the storm or be irrelevant. One scientist described the situation this way: imagine you are a doctor watching a patient's immune system fight off a virus. Sometimes the immune system wins quickly. Sometimes the virus gets through. From the outside, watching the same initial conditions, you cannot always predict which outcome comes next. The inner dynamics determine everything, and you cannot see those inner dynamics from outside the body. A hurricane's relationship with dry air works similarly. The storm's inner core dynamics determine whether the dry air intrusion becomes lethal or harmless, and the inner core is the hardest part of the system to observe. Researchers have been building higher resolution models specifically to simulate dry air interactions. Some progress has been made, but the models still struggle with the exact timing and intensity of dry air effects. What forecasters do know is that several rapid intensification events happened in part because dry air that was expected to weaken a storm failed to do so. The storm muscled through, the forecast weakening never came. The storm intensified instead. And while all of this was happening inside the atmosphere, something equally strange was happening to the storms themselves on the ground. They were slowing down, and the slower they moved, the more catastrophic they became. A hurricane moving at 15 miles per hour is dangerous. A hurricane moving at 2 miles per hour is a different kind of disaster entirely. The wind speeds can be identical, but the storm that barely moves does something the fast one cannot. It sits over one place and dumps rain continuously for hours, sometimes days. Rivers flood. Water rises in neighborhoods that wind speeds alone would never touch. People who survived the wind die in the flood. Scientists confirmed a troubling trend in the data. Tropical storms and hurricanes have been moving more slowly over land in recent decades. The average forward speed of Atlantic storms making landfall has dropped by roughly 10% since the middle of the last century. That sounds small. In practice, it is enormous. Here is the physics behind it. Hurricanes do not steer themselves. They are carried by large-scale atmospheric patterns called steering currents. These are broad rivers of air in the mid-levels of the atmosphere that push storms along their track. When steering currents are strong and clearly organized, storms move briskly. When the currents are weak or diffuse, storms wander or stall. Research suggests that the weakening of some large-scale atmospheric circulation patterns is connected to the broader warming of the climate system. The details are still being studied, but the slowing trend is confirmed in the observational record. The rainfall consequence is severe. A warmer atmosphere holds more moisture. This is basic physics, confirmed science. For every degree Fahrenheit of warming, the atmosphere can hold about 4% more water vapor. Warmer storms forming over warmer oceans draw up more moisture. They carry more water than historical storms of the same wind strength. When a storm carrying more water than ever before slows to a crawl over land, the rainfall totals become extraordinary. Studies comparing recent major storms to historical benchmarks found that some have dropped 20 to 30% more rain than a similar storm would have in the mid-20th century. That extra water has to go somewhere. It goes into rivers, streets, neighborhoods, and basements. The rain happens far from the coast too. Inland areas that historically had no reason to fear hurricanes find themselves under 10 or 15 inches of rain from a storm that made landfall 300 miles away. The flooding extends the disaster zone far beyond where emergency managers focused resources. Emergency planning models were built on historical storm behavior. They assumed storms moved at historically normal speeds. They were calibrated to historical rainfall rates. A storm that is slower and wetter than the historical baseline overloads those models. Resources get positioned for the expected impact zone. The actual impact zone is larger, slower, and soaked in more water than the plan accounted for. The clearest example of what a slow, wet storm does to a landscape came with a storm that practically stopped moving entirely. And it did not need extreme wind speeds to cause record devastation. September 2018. North Carolina, Hurricane Florence made landfall as a Category 1 storm. After days of forecasts showing a potential Category 4 strike, the wind speeds had dropped significantly. Some coverage suggested the worst was over. The wind threat was manageable. The water was not. Florence slowed to a crawl after making landfall. At its most sluggish, it was moving at 2 to 3 miles per hour. That is slower than a relaxed walking pace. A person strolling through a park moves faster than this storm was traveling across the Carolinas. For 2 days, Florence essentially parked itself over North Carolina and rained. The total rainfall in some locations, in a single storm, rivers that historically had never flooded reached levels that broke every record on their gauges. The Cape Fear River crested 8 feet above its previous record. Inland towns hours from the coast found themselves completely surrounded by water. The storm surge on the coast reached 11 feet in some areas. That wall of water pushed in from the ocean and stayed. It could not drain back because the rivers draining toward the ocean were running in reverse, flooded from rainfall upstream. The confirmed death toll from Florence exceeded 50 people. The economic damage crossed $17 billion, and a significant portion of that damage came from flooding in areas that emergency managers had not prioritized because they were far from the projected high wind zone. Florence became the case study that changed how meteorologists talk about hurricane danger. For decades, public communication focused on wind speed and category rating. Category 5 means extreme danger. Category 1 means less danger. Florence blew holes in that framing. A Category 1 storm with a historic rainfall event can be more destructive than a fast-moving Category 3. The National Hurricane Center and weather communicators began pushing hard to shift public attention toward flooding risk and rainfall totals, rather than just category. The category tells you about wind. It says nothing about how long the storm will sit and rain. What made Florence especially challenging was that its slowdown was partially predicted. Models showed the steering currents weakening. Forecasters warned that the storm would stall, but the message did not translate quickly enough into a shift in how the public understood the threat level. The category dropped. People relaxed. The rain did not. Florence confirmed what researchers had been warning about for years. The metric most people use to judge a hurricane's danger is increasingly misaligned with the actual threats that kill people and destroy communities. And the forces driving more moisture into these storms and more water into the atmosphere overall are only growing stronger. The atmosphere is a sponge. It absorbs water vapor constantly, and like any sponge, a warmer one holds more. This is not theory, it is physics. Scientists call it the Clausius-Clapeyron relationship. For every degree Fahrenheit the atmosphere warms, it can hold roughly 4% more water vapor. That relationship is confirmed, tested, and accepted across the scientific community. The atmosphere has already warmed. Global average surface temperatures are running more than 2 degrees Fahrenheit above the baseline from the mid-19th century. That warming is unevenly distributed. Ocean surfaces have absorbed the majority of the excess heat, and ocean surfaces are where hurricanes pull their moisture. Here is what this means in practical terms. A hurricane forming today over an ocean running 2 degrees warmer than it was 50 years ago is pulling water vapor from a hotter surface into an atmosphere that can hold more of it. The storm loads up with more moisture than an identical storm in 1970 would have carried. Research teams studying rainfall rates from recent major hurricanes compared their totals against historical storm archives. Storms with similar sizes, track speeds, and wind strengths. The recent storms consistently dropped more rain. Studies put the increase at somewhere between 7 and 9% for extreme rainfall events. 7 to 9% more water falling from the sky does not sound catastrophic in isolation. Spread across a watershed already close to flood stage, it is enough to push rivers over their banks and into neighborhoods. The geography of this matters. Coastal cities were built and planned when the atmosphere held less water. Drainage systems were designed to handle historical rainfall rates. Storm sewer capacity, river flood management infrastructure, and evacuation route elevations were all calibrated to a climate that no longer exists. A storm that fits within the historical envelope that infrastructure was built for causes manageable damage. A storm dropping 9% more rain than the historical maximum stresses every part of that system simultaneously. Roads flood that never flooded before. Drainage systems back up. The margins disappear. Forecasters are working with updated climate projections to adjust rainfall estimates for future storms. Some of the revised numbers are striking. Storms that would have been classified as 100-year flood events under historical conditions may now be occurring on 20-year or even 10-year timescales. There is one more layer to this. The extra moisture in the atmosphere does not just increase rainfall, it also releases more heat when it condenses inside a storm. More condensation means more energy released. More energy means stronger updrafts. Stronger updrafts pull more air upward through the storm, dropping the central pressure faster. More moisture feeds both the rainfall totals and the wind speeds simultaneously. Scientists are still working to quantify exactly how much of the intensification trend is attributable to increased atmospheric moisture versus other factors. The research is ongoing, but the direction of the effect is confirmed. And while all that extra energy is flowing through the storm, something unexpected happens inside the eye wall itself. Something that makes a hurricane briefly look like it is weakening, right before it gets dramatically stronger. A major hurricane has an eye. Everyone knows this. The calm center, the clear sky, the eerie stillness surrounded by the most violent winds on Earth. The eye is encircled by the eye wall, a towering ring of thunderstorms rotating around the center. This is where the storm's most extreme winds live. The inner edge of the eye wall marks the boundary where the wind speeds peak. Here is what most people do not know. That eye wall is not permanent. It breaks down, and when it does, the storm rebuilds a new one from the outside. Scientists call this the eye wall replacement cycle. It is a confirmed process regularly observed in major hurricanes, and it produces one of the most deceptive patterns in storm behavior. Here is how it works. As a hurricane intensifies, the eye wall contracts. It gets tighter and smaller. The winds concentrate into a narrower ring. This is actually associated with the most intense phase of the storm, but as the eye wall shrinks, it becomes less stable. Eventually, an outer ring of convection begins to form farther out from the center. This outer rain band starts stealing moisture and energy from the inner eye wall. The inner eye wall, now starved of resources, weakens. The storm's peak winds drop. The eye grows larger. To outside observers watching satellite imagery, it looks like the storm is falling apart. Then the outer ring closes into a complete ring. It becomes the new eye wall. It contracts inward. The storm re-intensifies. And it often comes back stronger than before. A full eye wall replacement cycle takes between 12 and 48 hours. During that time, the storm can weaken by 20 or 30 miles per hour, and then recover that strength and more. The challenge for forecasters is enormous. If a storm is approaching a coastline and begins an eye wall replacement cycle 18 hours before landfall, the models might project weakening. Emergency managers watching intensity fall might feel brief relief. Then the storm rebuilds and makes landfall stronger than the previous forecast suggested. Satellite technology has made the cycle more visible. Forecasters can now detect the double eye wall pattern, the original inner ring surrounded by a forming outer ring, on radar and enhanced satellite imagery. This allows them to tell the public that the storm is cycling, that apparent weakening is temporary, and that conditions may worsen again. But the timing of the re-intensification is still difficult to pin down precisely. Knowing the cycle is happening is different from knowing exactly when the new eye wall will fully form and how strong it will be. Some storms go through multiple replacement cycles during their lifetime. Each one produces a temporary weakening followed by a recovery. Each recovery can exceed the previous intensity peak. Tracking all of these cycles while simultaneously managing track uncertainty, rainfall estimates, surge projections, and landfall timing is exactly what hurricane forecasting centers do around the clock. And the tools they use to visualize all of these possibilities look nothing like the simple maps most people see on television. Turn on any news channel during hurricane season, and within minutes you will see the map. Dozens of squiggly colored lines extending from a central point and spreading outward like tangled string across the Atlantic or Gulf. This is a spaghetti plot, and what it actually represents is both more useful and more terrifying than most viewers realize. Each line on that map is a separate forecast model. Different countries run different models. The United States runs the Global Forecast System. Europe runs the European Center for Medium-Range Weather Forecasts model, widely considered the most accurate track model in the world. The United Kingdom, Canada, and several other nations run their own systems. Each model takes in the same basic observed data and solves its equations slightly differently. Each produces a different predicted track. When all those tracks are displayed together, you see the range of possibilities. When the lines cluster tightly together, forecasters have high confidence the storm will follow roughly that path. When the lines spread dramatically in different directions, the uncertainty is extreme. What scares meteorologists is not the spread itself, it is what the spread represents. Each diverging line means a model found a plausible atmospheric state where the storm goes somewhere different. Every direction those lines point is somewhere real people live. During Hurricane Sandy in 2012, the European model predicted days in advance that the storm would make a sharp left turn and strike New Jersey. Most American models predicted the storm would curve harmlessly out to sea. The spaghetti plot showed enormous disagreement. Forecasters at the National Hurricane Center faced a genuine dilemma. If they followed the European model, and it was wrong, they would cause massive disruption over nothing. If they dismissed it and it was right, the coast would have no warning. The European model was correct. Sandy devastated the Northeast. That event dramatically changed how forecasters communicate uncertainty. The spaghetti plot became more visible in public broadcasts. Media training programs for meteorologists started emphasizing the cone of uncertainty, the official graphic showing the probable track area, as a representation of a range rather than a guaranteed path. But here is the critical limitation that spaghetti plots do not show. They display track variability. They say nothing about intensity. You can look at a spaghetti plot where all the lines perfectly agree on the track and still have no idea whether the storm will be a Category 1 or a Category 5 when it arrives. The intensity uncertainty is invisible on the most watched forecast tool in public hurricane communication. Forecasters know this. They work to communicate intensity ranges alongside track probabilities, but the spaghetti plot image sticks in people's minds. The lines become the story. The strength of what is coming at the end of those lines gets less attention than it deserves. And sometimes the storm itself behaves in ways that no model predicted, no line anticipated, and no graphic prepared anyone for. What happens in the ocean when two of these massive storms come within range of each other is one of the most visually dramatic phenomena in meteorology. Two hurricanes, same ocean basin, close enough to feel each other. What happens next looks almost choreographed, and the results range from both storms weakening to one absorbing the other entirely. The Fujiwara effect is named after Sakuhei Fujiwara, a Japanese meteorologist who described the behavior of interacting vortices in 1921. His research was confirmed and expanded through decades of observation and modeling. The effect is real, repeatable, and genuinely strange to watch on satellite imagery. Here is the basic mechanism. Both storms are rotating vortices. Each one has a circulation that extends well beyond its visible cloud structure. When two storms come within roughly 900 miles of each other, their outer circulation fields begin to overlap. Each storm feels the rotation of the other. They begin to influence each other's movement. At that point, the two storms stop following their individual steering currents independently. They begin to orbit around a common center point between them. like two objects spinning around a shared axis. This orbital motion continues as long as the two storms remain close enough to interact. What happens next depends on the relative sizes and strengths of the two storms. If both storms are roughly equal in size and intensity, they orbit each other while gradually approaching. They may merge into a single larger system. The resulting merged storm is typically larger, but not necessarily stronger than either original storm. The energy from both circulations combines, but the combined system also has more internal disruption to overcome. If one storm is significantly stronger than the other, the outcome is more dramatic. The stronger storm essentially absorbs the weaker one. The dominant circulation wraps around the smaller storm and pulls it into its own rotation. The weaker storm stops existing as an independent system. It becomes part of the stronger storm's circulation. There is a third outcome. Two storms may interact enough to alter each other's tracks significantly without merging. One storm gets deflected northward, the other shifts east. Both continue on new paths neither would have followed without the interaction. For forecasters, the Fujiwara effect is a significant complication. When two active storms exist in the same basin simultaneously, every model run has to account for their interaction. The track forecasts for both storms carry additional uncertainty. The timing of the interaction matters enormously. If the stronger storm's circulation reaches the weaker, one a day earlier or later than predicted, the resulting tracks change completely. The Atlantic hurricane season of 2020 saw this happen with hurricanes Teddy and Paulette moving close to each other in the open Atlantic, with Teddy ultimately taking a modified track partially due to their interaction. Monitoring two simultaneous interacting systems while also managing all the other active Atlantic storms during a busy season is exactly the kind of operational nightmare that forecasters train for, but never fully get used to. The ocean is full of dynamics like this, hidden forces shaping storm behavior that are visible in the data, but nearly impossible to fully predict. One of those hidden forces is embedded in the storm's own pressure reading, and learning to read that number properly changes how dangerous a storm actually looks. Most hurricane coverage focuses on wind speed. Category ratings are built on wind speed. Evacuation orders reference wind speed. The entire public communication system about hurricane danger defaults to wind. But veteran meteorologists watch a different number more closely. The central pressure. Pressure is measured in millibars. Standard atmospheric pressure at sea level sits around 1,013 millibars. Inside a hurricane, the pressure at the center drops well below that. The lower the central pressure, the more extreme the pressure gradient between the storm's center and its surroundings. That gradient is what drives the winds. A steeper gradient produces faster winds. Here is why pressure matters more than wind speed in some situations. Pressure changes faster. Wind speed measurements have a built-in delay. The instruments measuring wind speed respond to what is happening right now in the immediate environment. Pressure in the storm center reflects the integrated state of the entire storm system. When the pressure drops rapidly, the storm's whole internal structure is reorganizing toward a more intense state. A storm with steadily dropping pressure is telling you it is still intensifying, even if the wind speeds have not yet caught up. A storm with rising pressure is weakening, even if the outer bands still look fierce on radar. Aircraft reconnaissance can measure central pressure directly using a dropsonde dropped through the eye. The lowest pressure reading found during a flight gives forecasters the most reliable current intensity estimate available. This number feeds directly into the official intensity forecast. The other thing pressure reveals is potential. A storm at 910 millibars central pressure has reached an extreme level of organization. The ocean's surface pressure gradient extends across the entire storm. The winds will be ferocious throughout the system, not just at the eye wall. Surge predictions, wave height estimates, and inland wind damage projections all scale with pressure as well as wind speed. Historical context helps. The lowest central pressure ever recorded in the Atlantic was inside Hurricane Wilma In 2005, it reached 882 millibars. That pressure reading remains the benchmark against which extreme Atlantic intensification is measured. During the most rapid intensification events, pressure falls at rates that experienced meteorologists describe as alarming, even when they have seen it before. A drop of 5 millibars per hour is considered extreme. Some storms have sustained drops of that rate for 8 or 10 consecutive hours. When forecasters see that happening in real time, the conversations in forecast centers change tone, because one recent storm dropped its pressure at exactly that rate, and what happened next gave veteran meteorologists a moment none of them will forget. October 2024, the Gulf of Mexico. Hurricane Milton existed as a Category 1 storm. Weather pattern analysis showed conditions were becoming favorable for strengthening. Forecasters issued intensity outlooks suggesting the storm would strengthen significantly over the coming days. What happened next happened faster than any model suggested. In 10 hours, Milton's central pressure dropped. 50 millibars in 10 hours. To translate that into something concrete, the pressure inside the storm fell by the equivalent of climbing from sea level to roughly 18,000 feet of altitude in less than half a day. The atmosphere inside that storm reorganized from the bottom up, in a window shorter than a typical workday. Milton went from a Category 1 hurricane to a Category 5 hurricane in a period of time shorter than it takes many people to get through a full night of sleep. A meteorologist who reviewed the pressure data publicly broke down emotionally on camera while discussing what the numbers meant for the people in the storm's path. That moment spread widely because it captured something that technical language cannot. Experienced scientists who spend their careers surrounded by extreme weather data were genuinely shaken by what they were seeing on their screens. The peak intensity Milton reached was extraordinary. Its central pressure bottomed out near 897 millibars. Its maximum sustained winds exceeded 180 miles per hour. It became one of the strongest hurricanes ever recorded in the Gulf of Mexico. Researchers studying Milton's rapid intensification found the same converging factors present in Otis. The Gulf of Mexico was running abnormally warm. Warm water extended unusually deep through the water column in the region Milton crossed. Wind shear collapsed at the same time the storm entered that warm water pool. The storm's internal structure was already well organized when conditions became perfectly favorable. The models had projected significant strengthening. They did not project the speed of that strengthening accurately. The gap between the forecast intensity curve and the observed intensity curve during Milton's most extreme phase represented a failure mode that forecasters and researchers recognized immediately. What made Milton particularly relevant beyond its own destruction was what it confirmed as a pattern. Otis had been explained partly as a geographic anomaly. Pacific storms approaching the Mexican coast have limited observation coverage. The argument could be made that the missing data explained the miss. Milton happened in the Gulf of Mexico, one of the most heavily monitored ocean basins on Earth. Hurricane Hunter aircraft flew into it. Satellite coverage was continuous. The observation network was as dense as it gets anywhere in the world, and the models still could not keep up with how fast the storm changed. For scientists, Milton closed the argument about whether Otis was a one-off data problem. It was not. Rapid intensification at this speed and scale can happen in the best monitored ocean basin in the world and still outrun the forecast system's ability to track it in real time. The implications for every coastal city in the Gulf and along the Atlantic seaboard are something forecasters think about every season, and the way those implications translate into human death is sometimes not through wind or surge. It is through the trees. September 2024, Hurricane Helene made landfall along the Florida Gulf Coast as a Category 4 storm. The wind was destructive. The surge was catastrophic along the coast. But when researchers tallied the confirmed wind-related deaths after the storm passed, one number stood out immediately: 61 out of 65 people killed by wind during Helene died because a tree fell on them. Not structural collapse, not flying debris from rooftops or signs. Trees. The same trees lining streets, shading yards, and bordering highways in every neighborhood across the southeast. This is not unique to Helene. Post-storm fatality studies consistently show that falling trees are among the leading causes of wind-related hurricane deaths. The data has been there for years. What Helene did was make the number impossible to ignore. Here is the physics. A mature hardwood tree in the southeast. A live oak or a water oak or a loblolly pine can stand 60 to 80 feet tall. Its root system spreads outward, not downward. In the sandy, often wet soils common across the coastal southeast, those roots sit in ground that gets saturated by storm rainfall before the peak winds even arrive. Saturated soil loses its grip. The roots have nothing firm to hold against. When sustained winds of 70, 80, or 90 miles per hour push against that saturated root system for hours, the physics are one-directional. The tree comes down. The problem is timing. People make decisions about shelter based on wind speed and category rating. A Category 4 landfall triggers widespread evacuation orders, but the wind-related deaths in Helene were not concentrated along the immediate coast, where evacuation compliance tends to be highest. They were scattered across inland areas, in neighborhoods where people sheltered in homes they believed were safe from a storm that had already crossed the coast. Those homes were safe from structural failure. They were not safe from a 60-foot tree landing on the roof. Emergency managers have struggled with how to communicate this risk. Telling people to stay away from trees during a hurricane is straightforward advice. Identifying which trees are likely to fall and in which direction is impossible at an individual level. The randomness of tree failure is part of what makes it so deadly. A family sheltering in an interior bathroom on the ground floor, following every piece of standard hurricane guidance, can still be killed if a tree falls across their roof at the exact right angle. Some communities have begun pre-storm tree assessments in areas with very high tree density, identifying trees with visible root damage, disease, or structural weakness, and removing them before hurricane season. The programs are expensive and cover a fraction of the trees in any given jurisdiction. The broader implication of the Helene data is about where people shelter and which interior rooms provide the most protection from overhead impact, which is different from which rooms protect against wind-driven wall failure. Rooms on lower floors with the smallest possible ceiling footprint are more survivable under a falling tree than a large open living room on an upper floor. Helene confirmed something researchers had documented, but the public had not fully absorbed. In modern hurricanes with increasingly extreme rainfall, which saturates soil and weakens root systems before peak winds arrive, trees are a primary lethal mechanism, and the scale of destruction these storms can deliver is straining the very system designed to categorize and communicate that danger, because some scientists now believe that system is fundamentally broken. The Saffir-Simpson hurricane wind scale runs from 1 to 5. Category 1 sits at 74 to 95 miles per hour. Category 5 covers everything at 157 miles per hour and above. No upper limit. No Category 6. That design was intentional. When the scale was created in the early 1970s, Category 5 represented a threshold so extreme that further subdivision seemed unnecessary. A Category 5 storm was the worst thing imaginable. The scale stopped there. The problem is that Category 5 now covers an enormous range of storm intensities. A storm with 160 miles per hour winds sits in the same category as a storm with 210 miles per hour winds. Both are labeled Category 5. Both trigger the same public guidance, but the destructive potential between those two storms is not even remotely comparable. A group of researchers published a paper in 2023 formally proposing a Category 6 designation for storms exceeding 192 miles per hour sustained winds. They argued that several recent storms would have qualified, Hurricane Patricia in 2015, which reached a peak intensity of 215 miles per hour over the open Pacific, would fall into the new category. So would Hurricane Wilma at its peak intensity. The scientific debate over this proposal cuts in two directions. Those who support a Category 6 argue that the current system fails to communicate the true danger of the most extreme storms. When everything above Category 5 gets lumped together, the public has no way to understand that some storms in that category are dramatically more dangerous than others. A scale that cannot distinguish between different levels of extreme creates a false ceiling. Those who oppose the change argue that adding a category would cause confusion without improving safety outcomes. The real problem, they say, is that people do not evacuate based on categories. They evacuate based on trust in local authorities, personal experience, and practical constraints like transportation and money. Adding a Category 6 does not solve any of those problems. There is a third concern. A Category 6 designation might actually reduce compliance for Category 5 storms. If people learn that Category 6 is the new worst, they may unconsciously recalibrate Category 5 as less dangerous than it actually is. The psychological effect could backfire. What everyone agrees on is that the current scale was built for a climate that no longer exists. The storms being observed today are reaching intensities that sit at the extreme edge of what the scale was designed to measure, and confirmed science shows that as ocean temperatures continue rising, storms in the highest intensity ranges will become more common. Whether the answer is a new category, a revised scale, or a completely different communication system is an active debate inside meteorology. The National Hurricane Center has not adopted Category 6. The conversation continues. What is confirmed is this: the storms at the top of the current scale are becoming more frequent. The tools built to warn people about them are struggling to keep up. And for the people who have to make the call on when to tell a city to leave, the timing problem gets more dangerous every year. A mandatory evacuation order for a major coastal city is one of the most logistically complex decisions in emergency management. It takes time for people to actually leave. Research on evacuation behavior shows that a significant portion of the population does not move until an order is issued. Once issued, the exodus begins. Cars fill the highways. Gas stations run dry. Lanes of traffic reverse direction to push capacity outward. In a city like Tampa or Houston or New Orleans, moving the population out takes 36 to 72 hours under good conditions. That window is the problem. Emergency managers need to issue evacuation orders before that window closes. If a storm is 48 hours from landfall and moving at 15 miles per hour, they have a rough estimate of when and where it arrives. They issue the order, the population moves. Now add rapid intensification to the scenario. A storm that looks like a Category 1 threat 48 hours out may not trigger a mandatory evacuation for large inland zones. The projected damage is significant, but survivable for people sheltering in solid structures. Emergency managers balance the enormous cost of a large evacuation, economic disruption, transportation accidents, fuel shortages, against the projected threat. For a Category 1, many decide to hold the broadest evacuation orders. Then the storm undergoes rapid intensification. 36 hours before landfall, it jumps to Category 3. 24 hours out, it reaches Category 4. The mandatory evacuation zone that should have been activated 2 days ago now needs to move within hours. The roads are already partially congested. Gas supplies are already strained from people who self-evacuated. The window to move the most vulnerable populations, the people in nursing homes, hospitals, and low-lying mobile homes, has compressed dramatically. This scenario has played out multiple times. Forecasters issue rapid intensification watches and warnings specifically to flag when conditions are favorable for this kind of sudden jump. The National Hurricane Center added a rapid intensification outlook to its advisory products to give emergency managers at least some forward notice. But the outlook requires knowing that conditions are favorable before the intensification begins. When conditions align suddenly and the storm jumps categories faster than the outlook anticipated, the warning lead time collapses anyway. Behavioral research on hurricane evacuation adds another layer of difficulty. People who evacuated for a previous storm and returned home to find minimal damage are statistically less likely to evacuate the next time. Previous experience with a storm that was forecast to be severe but turned out manageable erodes compliance for future orders. Emergency managers call this the cry wolf effect. Every unnecessary evacuation makes the next necessary one harder. Rapid intensification breaks the cry wolf effect in the worst direction. A storm that looked minor 24 hours ago and required no evacuation becomes a major hurricane requiring immediate action. The public sees a forecast that changed dramatically overnight and questions whether the new forecast is reliable or another false alarm. Building trust in rapidly changing forecasts while simultaneously moving millions of people in a compressed time frame is the operational challenge that keeps emergency managers working through nights when storms are developing. And part of why forecasts change so dramatically comes back to a problem in the sky above the storm. The satellites watching from space still have blind spots. Significant ones. From space, a hurricane looks spectacular. The swirling cloud structure, the clear eye, the spiral rain bands extending hundreds of miles outward. Satellites capture all of it in vivid detail. What satellites cannot see is what is happening inside the clouds. Modern weather satellites carry extraordinary instruments. Visible light cameras capture cloud structure with impressive resolution. Infrared sensors measure cloud top temperatures, which help scientists estimate how high and how powerful the storm's convection is. Microwave sensors can partially penetrate cloud layers to estimate precipitation rates and catch glimpses of the storm's inner structure. But the interior of a hurricane, the three-dimensional atmospheric structure from the surface to 10 miles up, remains largely invisible from orbit. Satellite instruments measure what they can detect from above. They see the tops of clouds. They infer what is happening below based on indirect signals. The actual wind speeds, humidity levels, and temperature gradients at different altitudes inside the storm are mostly estimated from those indirect signals, not measured directly. This matters enormously for rapid intensification prediction. The processes that trigger explosive intensification happen inside the storm's core, at altitudes and locations that satellite sensors struggle to reach. A small pocket of dry air at 7,000 feet above sea level, positioned just outside the eye wall, may be completely invisible on satellite imagery while still being capable of disrupting the entire intensification sequence. Geostationary satellites, the ones that orbit at a fixed point above the equator and provide continuous imagery, give forecasters a constant view of storm evolution. But they orbit 22,000 miles above Earth. At that distance, even the best instruments cannot resolve the fine-scale details that trigger rapid intensification. Low Earth orbit satellites pass over a given storm several times per day and carry more powerful instruments. But they only provide snapshots. A low orbit pass might catch a storm at its most organized state. The next pass comes 90 minutes later. In that 90-minute gap, something critical could change inside the storm and go undetected until the next snapshot. The gap between snapshots is exactly the timescale over which rapid intensification can begin. Researchers have proposed several solutions. A constellation of low Earth orbit satellites, specifically tuned for tropical storm observation, could reduce the snapshot gap to minutes. Satellite-based radar systems could penetrate cloud layers more effectively than current instruments. Improved microwave sounders could better characterize the three-dimensional moisture and temperature structure of the storm interior. All of these technologies either exist in prototype form or are confirmed feasible based on current engineering. The constraint is cost and launch capacity. Until the satellite constellation improves, the gaps remain. And in those gaps, storms evolve in ways that ground-based models cannot see and therefore cannot predict. The ocean below those storms is also full of hidden features that satellite observation cannot capture, and nowhere on Earth is that hidden ocean structure more dangerous than in one specific stretch of warm water. Enclosed bodies of water behave differently than open ocean. They heat up faster. They do not benefit from the deep cold water mixing that tempers temperature swings in the open Atlantic or Pacific. And the Gulf of Mexico, a semi-enclosed sea roughly 600 miles across and 900 miles from north to south, has been heating faster than almost any comparable body of water on Earth. The Gulf sits at the geographic convergence of every factor that drives rapid intensification. It is shallow enough along its northern rim to heat thoroughly during summer. It contains the loop current, that river of warm water flowing up from the Caribbean, along with a rotating family of warm water eddies that the current sheds throughout the season. Its geography means that storms entering from the Caribbean or forming within the basin have limited travel time before reaching land, compressing the warning window. And it is surrounded by some of the most densely populated and economically significant coastlines in the United States: the Texas Gulf Coast, the Louisiana coast, the Mississippi coast, the Alabama coast, and the Florida Gulf Coast together contain tens of millions of residents, vast petrochemical infrastructure, major port facilities, and critical energy production sites. A major hurricane tracking directly across the central Gulf toward any of these coastlines threatens not just local communities, but national supply chains. The loop current eddy system is particularly relevant for rapid intensification. When the loop current sheds an eddy, that eddy carries very warm, very deep water into the central Gulf. The eddy persists for months. It drifts slowly westward. Storms crossing that eddy encounter the same deep, warm water conditions that drove Katrina's explosive intensification in 2005. Researchers now map these eddies continuously. Satellite altimetry, a technology that measures the slight bulge in sea surface height caused by warm water below, allows scientists to track eddy positions and estimate their heat content. When a Gulf eddy sits in a storm's projected path, it appears in the forecast discussion as a factor favoring rapid intensification. But eddy positions shift. Storm tracks shift. The interaction between a storm and an eddy depends on exactly where the storm crosses and how quickly it moves. A storm tracking along the northern edge of an eddy gets different intensification potential than one crossing directly over its warm center. This precision in the ocean structure, the exact depth and temperature of specific water columns along a specific storm track, is beyond what models can perfectly simulate from satellite altimetry data alone. The Gulf's short distances also compress everything. A storm entering the Gulf from the Yucatan Channel, the narrow opening between Mexico and Cuba, can reach the Texas or Louisiana coast in 48 hours. If rapid intensification begins over the loop current eddy in the central Gulf, it may have 24 hours or less to play out before landfall. That is not enough time for a full evacuation of any major Gulf Coast city. What protects Gulf storms from growing stronger sometimes comes from an unexpected direction. Literally, from across the Atlantic Ocean, from the deserts of North Africa. And it works in a way that seems impossible until you understand the scale at which the atmosphere operates. Every summer, enormous plumes of dust rise off the Sahara Desert and drift westward across the Atlantic Ocean. The dust travels thousands of miles. It turns sunsets orange as far away as Florida. It settles into the Gulf of Mexico. It has been found in the soil of the Amazon rainforest. This dust is not just a visual phenomenon, it carries a layer of air with it, and that layer can stop Atlantic hurricanes before they even begin. Scientists call it the Saharan air layer. It is a mass of very warm, very dry air that sits between roughly 5,000 and 15,000 feet above sea level. This layer forms over the desert as superheated surface air rises and spreads outward. Winds carry it off the African coast in pulses, typically every few days during summer and early fall. When the Saharan air layer pushes into the main Atlantic hurricane development region, the effects on tropical disturbances are significant and confirmed. The dry air embedded in the layer suppresses storm development directly. Tropical disturbances need a moist, unstable atmosphere to organize into tropical storms. When the Saharan air layer pushes that moist air aside and replaces it with hot, dry air, the development process stalls. The thunderstorm activity that would normally build a circulation gets choked off. The dust itself also plays a role. Dust particles absorb incoming solar radiation, warming the Saharan air layer, but reducing the amount of sunlight reaching the ocean surface below. Less sunlight means slightly lower ocean heating. The fuel supply for a developing storm gets reduced from both above and below simultaneously. During years when the Saharan air layer is exceptionally active, Atlantic hurricane season can run below expectations even when other large-scale conditions seem favorable. Forecasters track the layer's position and intensity as a seasonal suppression factor. The flip side is equally important. When the Saharan air layer weakens or shifts northward, the main development region opens up. Moist, unstable air floods back in. Tropical disturbances find an environment suddenly favorable for rapid development. Season activity can spike within days of the Saharan air layer retreating. This is why some of the busiest Atlantic hurricane bursts happened quickly after a quiet period. The Saharan air layer was suppressing activity. When it pulled back, several disturbances that had been sitting in unfavorable conditions suddenly found open air. The layer also interacts with storms that have already formed. A strong hurricane can push through the dry air layer. Its circulation is powerful enough to maintain structure even as dry air intrudes around its edges. But a weaker storm or a developing disturbance has far less resistance. The dry air wins. The storm falls apart. Scientists continue studying the Saharan air layer as part of the broader seasonal forecasting picture. Its behavior varies year to year. Its pulsing nature creates windows of active and suppressed hurricane development that repeat throughout the season. Those windows, and the uncertainties about why some storms survive conditions that destroy others, lead directly to one of the deepest unsolved problems in hurricane science. Two storms, same ocean, same wind shear environment. One survives and intensifies, the other falls apart within hours. This happens. Scientists have documented it, and they cannot fully explain it. Wind shear tears at a hurricane by tilting its circulation, disrupting its eye wall, and preventing the efficient outflow that the storm needs to sustain itself. The destructive mechanism is understood. The physics are confirmed. High shear should weaken and destroy tropical systems. In most cases it does, but in some cases, something inside the storm resists. Researchers studying these cases found that storms with particularly intense, concentrated inner cores seem to have more resilience against shear than looser, broader systems. A compact, intensely organized eye wall creates a self-reinforcing circulation that can partially hold itself together even as shear tries to tilt and tear it apart. The storm essentially fights back. This property is sometimes called intrinsic intensity. A storm with very high intrinsic intensity has a tight energy core that does not depend as heavily on perfect atmospheric conditions to maintain itself. It can sustain its structure through environmental stress that would destroy a weaker, less organized system. The problem for forecasters is measuring intrinsic intensity accurately. It requires detailed data about wind distribution inside the eye wall, the temperature and pressure structure of the eye itself, and the vertical tilt of the storm's circulation at multiple levels. All of this requires direct aircraft observation, and aircraft do not observe every storm at every moment. When a storm enters a high-shear environment without recent detailed reconnaissance data, forecasters have to estimate its intrinsic intensity from satellite imagery and model output. Those estimates carry significant uncertainty. A storm that looks moderately organized from above may have a much more intense inner core than satellite signatures suggest. The result is that some storms that models forecast to weaken dramatically in response to shear instead survive and maintain their strength. They arrive at coastlines stronger than expected. Warnings issued for a weakening system turn out to be dangerously conservative. Researchers confirmed another factor complicating this picture. The ocean temperature under a sheared storm also influences survival. A storm being torn apart by shear over very warm water gets a constant energy input that partially compensates for the disruption. The warm water keeps feeding the inner core even while shear tries to destabilize it. This interaction means that shear forecasts, made without accounting for the exact ocean temperature under the storm's track, can produce intensity errors in either direction. There is also a timing element. A storm entering high shear at its weakest point in an eye-wall replacement cycle is more vulnerable than one entering the same shear at its most organized phase. Two identical storms entering identical shear at different points in their internal cycles can respond completely differently. All of these factors compound the intensity forecast problem. Each one is a variable the models handle imperfectly. Together, they create a situation where intensity forecasts carry inherent uncertainty that no current technology fully resolves. What governs whether any individual season will produce many storms, likely to test these limits, is itself a matter of ongoing scientific debate, and it involves a natural cycle operating on a timescale most people have never heard of. The Atlantic Ocean breathes on a long cycle. Over periods of roughly 20 to 40 years, average sea surface temperatures across the North Atlantic shift between warmer and cooler phases. Scientists call this the Atlantic multi-decadal oscillation. During its warm phase, hurricane activity in the Atlantic tends to increase. During its cool phase, it tends to decrease. The pattern is confirmed in historical records stretching back centuries through proxy data from coral cores, tree rings, and sediment layers. The Atlantic entered a warm phase around 1995. That transition corresponded with a dramatic increase in Atlantic hurricane activity that continues to the present. The active seasons from 2000 through today, with their numerous intense storms and record-breaking events, occurred during this warm phase. The debate among scientists is significant, confirmed, and consequential. One side argues that the Atlantic multi-decadal oscillation is the primary driver of the increased hurricane activity since 1995, and that a natural shift to a cool phase will eventually reduce activity back toward quieter baselines. On this view, the current era of intense storms is partly a natural cycle, and climate change is one factor among several. The other side argues that the oscillation itself is being modified by climate change. The warm phase is running warmer than historical warm phases. The heat driving the current active era is not just natural oscillation, but natural oscillation amplified by decades of ocean warming from greenhouse gas emissions. On this view, even when the oscillation eventually shifts to its cool phase, the cooler temperatures will be warmer than the cool phases of the past century. The baseline keeps rising. The practical implication depends on which view is closer to correct. If natural oscillation is the dominant driver, a cool phase transition could bring relative relief. If climate change has fundamentally altered the baseline, a cool phase transition provides less protection than historical patterns suggest. Current research leans toward the second interpretation. The sea surface temperatures fueling Atlantic hurricane activity are running higher than any previous warm phase on record. That excess above historical warm phase levels is consistent with a climate change signal layered on top of natural variability. For communities planning infrastructure, emergency management systems, and coastal development over the next several decades, the distinction matters enormously. Planning for a natural cycle that will ease has very different implications than planning for a permanently elevated baseline. What nobody debates is the experience of flying directly into the center of these storms. The aircraft that gather data from inside a hurricane encounter something that no satellite image or model output can fully capture. The eye of a major hurricane is one of the strangest places on Earth. The eye of a major hurricane is roughly 10 to 20 miles across, sometimes larger. Inside it, the winds drop dramatically, the sky often clears, sunlight reaches the surface, the ocean below, churned into a chaos of crossing swells from every direction, still rages. But overhead, the air is calm. Hurricane hunters describe flying into the eye as one of the most disorienting experiences in aviation. The aircraft batters through the eye wall, thrown violently by the most extreme turbulence in the atmosphere. Then, within seconds of crossing into the eye, everything quiets. The ride smooths out. The crew can stand up. They look out the windows and see blue sky above and a ring of towering thunderstorms surrounding them on all sides. The physics of the eye involves a process called subsidence. Air that rises through the eye wall and flows outward at the top of the storm must be replaced. In the eye, air descends from higher altitudes to fill that space. Descending air compresses and warms. Warm descending air suppresses cloud formation. The eye stays mostly clear. The warmth inside the eye is measurable and dramatic. At the surface level, the eye of a Category 5 hurricane can be 15 to 20 degrees Fahrenheit warmer than the surrounding environment. This warm core structure is what makes tropical cyclones fundamentally different from cold core systems like winter storms. The warm core is the engine's heart. It is what makes hurricanes intensify rapidly when conditions allow. Satellite instruments can detect the warm core by measuring temperatures at high altitudes in the eye. A strengthening warm core means the storm is intensifying. A cooling warm core means the storm is weakening. This remote detection capability gives forecasters a continuous window into storm intensity changes between aircraft reconnaissance missions. Inside the eye, the ocean is visible, and it is extraordinary. Swells generated by the surrounding eye wall arrive from all directions simultaneously. They collide, producing pyramidal waves that rise 20 or 30 feet with no consistent direction. Ships caught in the eye of a major hurricane face this chaotic sea state from every angle at once, which is more structurally damaging to vessels than directional waves of equal height. The eye also moves. As the storm tracks forward, the eye passes over any fixed point within minutes. The experience of the eye passing over land is a sudden, brief respite in the middle of a catastrophe. People emerge from shelter into apparent calm. They do not always understand that the eye wall is still approaching from the other side. Post-storm fatality data includes deaths that occurred when people emerged during the eye passage and were caught in the returning eye wall. The eye wall itself, surrounding that strange calm center, generates the storm surge that historically kills more people than wind ever does. And the mechanics of storm surge are misunderstood by most people who live in its path. Wind gets the headlines, storm surge gets the casualties. Storm surge is the abnormal rise of ocean water driven by a hurricane's winds and low pressure. It is a dome of water that the storm pushes ahead of itself as it approaches the coast. When that dome reaches shallow coastal waters and finally makes landfall, it crashes ashore as a wall of moving seawater that can rise 10, 15, or 20 feet above normal sea level within minutes. The physics behind it starts offshore. A hurricane's circular wind pattern drives water toward the center of the storm at the ocean surface. As the storm approaches land, that accumulated water has nowhere to go except forward onto the coast. The geometry of the coastline concentrates it. A bay or inlet that funnels the surge into a narrowing funnel amplifies the water height dramatically. The low central pressure also contributes. Lower atmospheric pressure allows the ocean surface to bulge upward. A 1 millibar drop in pressure corresponds roughly to a 1 centimeter rise in sea level. For a storm with a central pressure 60 or 70 millibars below ambient, that effect adds meaningful height to the surge. The result is water that arrives fast, rises quickly, and carries enormous momentum. A column of seawater moving inland at 10 miles per hour and rising at 2 feet per minute, does not behave like a gentle flood. It is a battering force that pushes walls off foundations, sweeps cars off roads, and overwhelms anyone unable to escape to higher ground before it arrives. The most lethal surge events in American history share two characteristics. They struck coastlines with very shallow offshore water, which amplifies surge height as it approaches land, and they struck with insufficient warning time for full evacuation. Hurricane Katrina produced a surge exceeding 25 feet in parts of Mississippi. That figure is roughly the height of a 2-story house. People in the surge zone who did not evacuate faced water rising above the roof lines of standard residential structures. Attic survival was the only option. Some made it, many did not. Storm surge is also invisible in pre-storm coverage in a way that wind is not. Wind damage is immediate and visible. A camera crew filming horizontal rain and flying debris captures something viscerally dangerous. Storm surge is water, and water arriving at night or behind tree lines provides no dramatic visual warning before it strikes. Forecasters have pushed hard to improve surge messaging. The National Hurricane Center produces storm surge watches and warnings that are separate from hurricane watches and warnings. Surge inundation maps show specific neighborhoods at risk from specific feet of surge, rather than just coastal distance from the track. These tools are better than what existed 20 years ago, but surge mapping depends on accurate storm track and intensity forecasts at landfall. When rapid intensification changes the storm's strength in the final 24 hours, the surge projection changes with it. A storm that intensifies from Category 2 to Category 4 in the hours before landfall produces dramatically more surge than the earlier forecast suggested. The body of water that feeds the worst surge events along the American East Coast has a less obvious connection to these storms than most people realize. The Gulf Stream is a river of warm water moving through the Atlantic Ocean. It originates in the Gulf of Mexico, flows through the Florida Straits between Florida and Cuba, runs northward along the east coast of the United States, and eventually curves toward Europe. The surface current is powerful enough to move roughly 30 times the combined flow of all rivers on Earth. It carries tropical warmth northward along a coastline that would otherwise be significantly cooler. It is one of the primary reasons that European climates are milder than their latitudes would suggest. For hurricane forecasting, the Gulf Stream matters in a specific and documented way. Storms tracking northward along the east coast follow a path that often runs parallel to or directly over the Gulf Stream. The warm water of the Gulf Stream, running between 78 and 84 degrees Fahrenheit along much of the east coast during hurricane season, provides a continuous fuel source for storms moving through the region. A storm that might weaken over cooler offshore waters instead maintains its strength or intensifies as it tracks over Gulf Stream waters. This has produced major hurricanes striking further north along the east coast than people historically associated with catastrophic tropical weather. The Gulf Stream is also warming. Long-term ocean temperature records show that the Gulf Stream's surface temperatures have increased along the east coast corridor. The band of water warm enough to sustain hurricane strength now extends further north and remains warm later into the calendar year than it did several decades ago. Research on future hurricane tracks suggests this warming extends the geographic range of potential major hurricane impacts. Cities like New York, Boston, and the coastal areas of New England, which have historically faced tropical storms, but rarely major hurricanes, sit in a region where the Gulf Stream's warming is most pronounced. The probability of a major hurricane maintaining intensity far enough north to threaten these areas is higher than historical data alone suggests. Hurricane Sandy in 2012 was not a major hurricane at landfall. Its wind speeds had decreased, but it made landfall at an unusual angle, driven by a combination of steering currents, and its storm surge impacted areas of New York and New Jersey that had no prior experience with tropical surge flooding. The damage ran into $65 billion. Sandy was not running on Gulf Stream warmth alone, but its track along and across the Gulf Stream corridor kept it organized longer than it might otherwise have remained. The storm maintained enough structure to produce catastrophic surge at an unprecedented location. The built environment along that corridor reflects a historical understanding of hurricane risk that is becoming outdated. The people and infrastructure now standing in the expanding threat zone were placed there based on assumptions about the climate that are no longer accurate. The cost of that mismatch between historical risk and current reality shows up every time a major storm makes landfall. And that cost has grown dramatically because of decisions made about development that have nothing to do with weather science. A hurricane striking the same coastline 50 years apart can be identical in physical intensity and produce completely different levels of economic damage. The storm did not change. What changed is everything the storm hit. The United States coastline has undergone massive development since the mid-20th century. Barrier islands that were largely undeveloped in 1970 are now covered with high-density residential construction. Coastal wetlands that historically absorbed storm surge energy have been drained and filled for development. Floodplains that provided natural buffers against inland flooding now contain subdivisions, shopping centres, and roads. This is not a theory, it is confirmed in the damage data. Researchers comparing economic losses from storms of similar intensity across different decades found that exposure, meaning the value of what sits in harm's way, has grown far faster than storm frequency or intensity. A Category 3 hurricane striking a developed barrier island in 2024 causes multiples of the economic damage that the same storm caused in 1974, simply because of how much more is now there to destroy. Population growth in coastal counties accelerated significantly beginning in the 1980s. Warm weather, ocean views, and lower land prices compared to established inland metros drew millions of residents. Many settled in areas that historical data showed were struck by major storms every few decades. The few decades passed, the storms came back, the wetland loss is particularly significant for flood dynamics. Coastal wetlands, including marshes, mangroves, and cypress swamps, act as natural surge breaks. Water moving inland through healthy wetlands loses energy through friction and absorption. Studies of Louisiana and Florida coastlines found that intact wetland belts could reduce surge height measurably over distances of several miles. Those belts have shrunk dramatically across much of the Gulf Coast. Storm surge now moves inland with less resistance than it encountered 30 or 40 years ago. It reaches further. It rises higher in areas that once had natural protection. The economic model for coastal development also creates a feedback loop that resists correction. Property values in coastal zones reflect demand that does not fully price in long-term storm risk. Federal flood insurance programs have historically subsidized coverage in flood-prone areas at rates that do not reflect actuarial risk. This made living in high-risk zones cheaper than it should have been, encouraging more development in exactly the areas most vulnerable to intensifying storms. Those subsidy structures are changing. Flood insurance reform and updated risk maps have raised premiums sharply in some of the most vulnerable areas. Some property owners are finding that insurance costs are making coastal properties economically unviable. The adjustment is painful and inequitable. It hits lower-income homeowners hardest. The scientists watching these storms know that the damage totals climbing every decade reflect not just changing storms, but a society that built itself into the path of intensifying weather and is only now beginning to reckon with that decision. And the people communicating the danger of these storms are facing a threat that has nothing to do with the weather. In August 2024, a retired meteorologist who had spent decades at the National Hurricane Center told reporters that former colleagues were receiving threatening messages from members of the public. The threats came after forecasts that proved inaccurate, or after storms that caused less damage in a specific location than predicted. This is confirmed. Multiple meteorologists have publicly described receiving harassment, threatening emails, and abuse on social media following high-profile forecast events. The National Weather Service issued statements about the pattern. Professional meteorological organizations addressed it publicly. The social media environment around major hurricane events has changed substantially in the past decade. Conspiracy theories about storm manipulation, government weather control, and deliberate exaggeration of threats circulate widely during active storm periods. When a forecast storm turns out to be less severe than projected in a specific location, these narratives gain traction among some audiences. The meteorologists who issued the forecast become targets. The irony embedded in this dynamic is severe. Forecast uncertainty is a real and documented feature of hurricane prediction. Forecasters communicate that uncertainty explicitly through cones of uncertainty, probability graphics, and explicit statements about forecast confidence. A storm that makes landfall 40 miles from the projected track center still falls within the documented uncertainty of a standard forecast. The forecast was not wrong. The storm landed where the forecast said it might. But simplified media coverage that focuses on a single track line without conveying the probability range trains audiences to expect precision that the science cannot provide. When reality diverges from the depicted centerline, it looks like a failure even when it is not. The consequence for public safety is documented and serious. Meteorologists who fear public backlash may become more conservative in how they communicate uncertainty. They may soften language about extreme scenarios to avoid seeming alarmist. Institutions become cautious about how strongly they warn about worst-case outcomes. For rapid intensification specifically, where the worst case can materialize in hours and where communication of extreme scenarios is most critical, any softening of uncertainty language represents a direct public safety problem. The time when forecasters most need to communicate maximum danger clearly is exactly when the political and social pressure to avoid alarming people is highest. Researchers studying hurricane risk communication identified this tension explicitly. The public needs forecasters to be both accurate and willing to emphasize extreme possibilities. The current environment makes both simultaneously harder, and the technology being developed to eventually resolve the core forecasting limitations may represent the biggest shift in hurricane prediction in decades. It uses a kind of mathematics that no human fully understands, and it is already producing results. Traditional weather models work by solving equations. Scientists encode the known laws of physics into mathematical formulas. The model solves those formulas across thousands of grid points, thousands of times per second, stepping forward through time to produce a forecast. The approach is transparent. Researchers can inspect why the model produced a specific output. They can identify errors in the physics and correct them. Artificial intelligence models work differently. They learn patterns from data without being explicitly told the rules. A system trained on decades of hurricane observations and corresponding atmospheric conditions learns to recognize the combinations of factors that precede rapid intensification. It does not solve physics equations. It identifies statistical patterns that physics equations are too coarse to capture. Several research groups and major technology companies published results in 2023 and 2024 showing that artificial intelligence weather models could match or exceed traditional models on track forecasting at a fraction of the computational cost. Google's GraphCast model and the European Centre's own artificial intelligence experiments produced track forecasts comparable to their best operational models while running thousands of times faster. For intensity forecasting, the results are more complicated and more promising simultaneously. Traditional models consistently underperform on rapid intensification because the triggering processes are too small scale for their physics grids. Artificial intelligence systems trained specifically on high-resolution data around rapid intensification events show some ability to identify precursor signatures that traditional models miss. What makes this genuinely significant is the speed difference. A traditional supercomputer model taking hours to run a single forecast cycle can be run in seconds using an artificial intelligence system on standard hardware. That speed enables something traditional forecasting cannot do in operational timescales. running thousands of forecast variations simultaneously, with small differences in starting conditions, to build a fuller picture of the range of possible outcomes. This ensemble approach is not new in meteorology. Traditional ensemble forecasts already run multiple model versions, but the number of members in a traditional ensemble is constrained by computational cost. An artificial intelligence system could run 10,000 slightly different versions of a forecast in the time a traditional system completes one run. The resulting probability distributions for storm intensity would be far more detailed than anything currently available. The limitation is data. Artificial intelligence models learn from historical observations. For rapid intensification specifically, the historical database of well-observed events is smaller than researchers would like. Events like Otis and Milton, where high-quality reconnaissance data exists alongside satellite observations and model output, are exactly the training material these systems need. Each new well-documented event makes the next generation of models better. Researchers are also exploring hybrid systems where artificial intelligence handles the pattern recognition, while traditional physics models handle the dynamics. The hybrid approach attempts to capture the best of both methods. Operational deployment of these systems is happening incrementally. Some artificial intelligence guidance is already being used by forecasters as supplementary information alongside traditional model output. Full operational integration is a near-term rather than distant possibility. Whether it arrives in time to meaningfully change the outcome the next time a storm like Otis or Milton forms over warm water with dropping shear is the question that matters most. Everything discussed in this series exists simultaneously: the warming ocean, the deepening warm water layers, the dropping shear windows, the satellite blind spots, the model limitations, the compressed evacuation timelines, the growing coastal population sitting in the surge zones. They do not occur in sequence, they converge. The scenario that concerns researchers most is not a storm that behaves unusually. It is a storm that behaves exactly as the science now predicts, in a location and on a timeline that the current forecasting system cannot handle. Picture a tropical disturbance forming in the central Gulf of Mexico in late September. Sea surface temperatures in the central Gulf are running 3 degrees above the historical average for that time of year. A warm water eddy shed by the loop current sits directly in the disturbance's projected path. Wind shear in the region is dropping as an upper-level high-pressure system strengthens to the north. The disturbance organizes into a tropical storm overnight. Models show a storm tracking toward the northern Gulf Coast over the next 72 hours. Initial intensity forecasts suggest it could reach Category 2 strength, potentially Category 3 if conditions remain favorable. Emergency managers in coastal counties begin preparatory actions. Some voluntary evacuation orders go out for the most vulnerable surge zones. Then the storm crosses the warm eddy. The break that would normally cool the surface water does not engage. Wind shear drops to near zero over the eddy. The storm's inner core contracts. In 12 hours, sustained winds go from 70 miles per hour to 140 miles per hour. The mandatory evacuation orders come out now, but the storm is 36 hours from landfall, the evacuation window that emergency managers assumed they had just collapsed by a day. The coastal highway network, already partially loaded with voluntary evacuees from earlier orders, cannot process a full mandatory evacuation in 36 hours. Traffic backs up. Gas runs out. People who left too late to get ahead of the storm stop moving. This is not a worst-case fantasy. It is a composite of documented conditions that have already occurred separately. The eddy was there before Katrina. The shear collapse happened before Otis. The compressed warning window played out before Milton. What has not yet happened is all of them combined for a major population center at exactly the wrong time. The population of Tampa Bay, for example, sits in one of the most surge-vulnerable metro areas in the United States. Detailed surge modeling shows that a direct major hurricane strike could produce water levels that reach several miles inland across low-lying terrain. A full evacuation of that region takes an estimated 72 hours under good conditions. The storms that produce those surge levels can now organize and intensify in less time than that evacuation requires. Forecasters know this. Emergency managers know this. Researchers who model these scenarios know this. The gap between what the science now shows is possible and what the response system can handle in the time available is documented, confirmed, and growing. The question of what happens next, for forecasting, for coastal planning, for the science itself, is something researchers are working on now. And the answers coming out of that work are more complicated than either optimism or despair can capture. The people working on this problem are not standing still. Forecasting centers around the world are investing in higher resolution models that simulate storm dynamics at finer scales. Where current operational models use grid squares covering 20 or 30 miles, next-generation systems are pushing toward grids of 3 miles or less. At that resolution, the mesoscale processes that trigger rapid intensification become visible to the model. The small pockets of dry air, the subtle inner core reorganizations, the precise interaction between a storm and an ocean eddy start to appear in the simulation. These finer grids demand more computing power. The investment in supercomputing infrastructure at NOAA and at international meteorological agencies is ongoing. Some of the new computing capacity is already operational. More is scheduled. The Ocean Observation Network is also expanding. More Argo floats are being deployed across the Atlantic and Gulf basins. Their temperature and salinity profiles feed directly into the ocean initialization that models use at the start of each forecast run. Better ocean data means the model starts with a more accurate picture of where the deep, warm water sits before the storm even arrives. Uncrewed aerial vehicles are moving from experimental to operational status. Prototypes have flown into actual storms. The first generation of operational hurricane observation drones is expected to supplement crewed aircraft reconnaissance in the coming years. They can fly lower altitudes, remain on station longer, and sample parts of the storm that crewed aircraft cannot safely access. The artificial intelligence systems are integrating faster than traditional model updates historically have. The development cycle for artificial intelligence guidance is shorter. Updates happen in months rather than the years that major physics model upgrades require. Each major storm event that generates high-quality observation data becomes new training material that improves the next generation of guidance. Public communication is changing too. The National Hurricane Center is shifting emphasis from category-focused messaging toward impact-based messaging. Rather than leading with Category 4, the communication leads with what that storm produces. 20 feet of surge in these specific neighborhoods. 15 inches of rain across this specific river watershed. Tree failure risk in these wind speed zones. The category becomes one number among several, rather than the headline that determines how people respond. Some coastal jurisdictions are investing in earlier and more aggressive pre-positioning of evacuation resources. Rather than waiting for a track to solidify before beginning evacuations, some plans now trigger preemptive action based on favorable conditions for rapid intensification, even before a storm has intensified, moving vulnerable populations out of surge zones before the storm organizes rather than after it becomes a Category 4. This approach has costs. Resources spent on an evacuation that turns out to be unnecessary are significant. Political and public tolerance for early evacuations that precede storms that never materialize is limited. But the alternative, waiting for certainty that the current science cannot deliver, consistently produces the narrow warning windows and compressed evacuation timelines that have characterized the most catastrophic modern landfalls. The future of every coastal city in the hurricane belt runs through this set of trade-offs. Better science, better tools, better communication, faster decisions with less certainty. more preparation before confirmation arrives. The ocean is warmer, the storms are stronger, the warning system is improving, but has not closed the gap with the threat it faces. Every improvement in rapid intensification forecasting represents time. Time to move people, time to position resources, time to make decisions before they become impossible. That time is what forecasters are fighting for, one storm at a time, one season at a time. And the ocean is not waiting.